So this is the back side of the review, starting with problems 14 all the way through 20. We'll only be using a calculator for the for number 20, which is going to make 14 and 15 a bit of a challenge because they don't give us the ability to use a calculator, but we don't really need it too much. If you're following along, just got to draw a quick sketch of a graph. So for 14, we're asked to find the area between the region bounded by the graphs of x square root of x plus 2, x equals 0, y equals negative 1, and x equals 4. And that's not going to be too tough if we just draw a picture of it real quick. So off to the side or on a different piece of paper, I'm just going to make a quick sketch of this graph. X equals 0 and x equals 4, those are just going to be kind of the goalposts on the x-axis. Y equals negative 1, so I'm going to have, let's see, 1, 2, 3, 4. So we've got kind of a boundary coming down here. This is x equals 4. There's x equals 0. Y equals negative 1 would be like this, down here. And the square root of x plus 2, if I graph that really quick, I'm just going to think about some numbers. I know the square root of 0 plus 2 is 2. Oh, hang on, I got to do a thing really quick. Thanks for letting me know. I was buried in my own little work there. I have to have the window be active, otherwise it won't show up in this program. That's why.
It sounded really profound.
Yeah, what's that?
It sounded really profound, though.
Hey, that's the way it goes. You know, speaking of profound, I was talking to my one of my classes, and one of my favorite literature quotes of all time is the opening line of Anna Karenina by Leo Tolstoy, which is that happy families are all alike, but unhappy families are all unhappy in their own unique way. Always like that. It's a really good quote. Squared. What's that? Not yet. I can when I'm done with this recording. Yes. Okay. Yeah, sorry. Let's see. As far as the square root of x plus 2, I'm just kind of thinking out loud about a few key points. I know that the square root of 1 is 1 plus 2 is 3, and the square root of 4 is 2 plus 2 would be 4. So that curve looks kind of like this. So if you sketch it all out, all 4 of those boundary lines, you're looking at kind of this area right here. That's the chunk that we're going to find the area of. And we're not allowed to use a calculator on this one, so we got to kind of use our just our knowledge of integrals and setting things up. And we're going to do it by hand. But the good news is we can pretty easily divide this up vertically by using a dx rectangle. This would be the square root of x plus 2 on top minus negative 1 on bottom. I'll draw that in a little more detail over here. This would be the integral from 0 to 4 because of our goalposts on the left and right side of it, 0 to 4. And the height of every one of those rectangles is just the square root of x plus 2 minus negative 1. And we can simplify that in a minute, but right now I'm going to leave it just as it currently looks. Just like that. So let's go ahead and clean that up a little bit. That's a minus negative 1, so really this is the integral from 0 to 4 of the square root of x plus 3 dx. And we'll just run this through our the way we evaluate integrals, which is by finding the antiderivative and plugging in 4 and plugging in 0. The good news is whenever you get 0 as one of your starting values, that usually makes these problems a lot easier because if we take the antiderivative of this, every term is going to have an x in it, so 0 we can just kind of ignore. It might be helpful to think about this as x to the 1/2 power plus 3, just to make the antiderivative a little more clear. So the antiderivative here is going to be x to the 3/2 power. So we're going to have to go add 1 to 1/2. And then what we need in front is a fraction that will cancel out 3/2 when we take it down. And so that's going to be 2/3. And I like to write this kind of like that. 2 times x to the 3/2 power over 3. And if you run that through the power rule, the 3/2 will come down, cancel out the 2/3, and then leave x to the 1/2, which is exactly what you need. That's a pretty tricky antiderivative, but it's also super common. And then 3x goes there. And then we're going to evaluate this from 4 to 0, which again is really easy because plugging in 0 doesn't do anything. It'll just make the whole thing 0. So really we just got to plug in 4 and call it a day for this answer. So I'm going to do this underneath here. We're going to have 2 times 4 to the 3/2 power over 3 plus 3 times 4. And technically there is a minus 0 on the end of this thing, but I'm just going to leave that off there for now. As far as 4 to the 3/2 power, well, 4 to the 1/2 power is 2, and then 2 to the 3rd power is 8, and then 2 times 8 is 16. So this is 16 thirds plus 12, which could be thought about as 16 thirds plus 36 thirds, which is 52 thirds. And I like that answer the best. So far, this is the longest problem on the review. Does 52 divide by 3 evenly? I don't think so. We're not allowed to use a calculator either, so. Uh-oh. Karen's just checking. That's all right. I don't think it does. No. That's it. Okay, cool. Then I would leave as a fraction. The next question is very similar, so we're going to handle it pretty much the exact same way. We're going to very carefully sketch a graph of, do we have just 2 functions this time? Oh no, we have y equals 0 also. We're going to sketch a real quick graph of what that would look like, x plus 2 squared, 4 plus x, and y equals 0, and then we're going to think about how we could possibly find the boundary or the area of that. So let's do this one maybe off to the side. I'm going to get some more room for myself here. This is number 15. Our 3 functions are x plus 2 squared, x plus 4, or 4 plus x, and y equals 0. So the first challenge here is to really sketch a graph of all 3 of these and see kind of where they cross, because since we don't have any other clues, we have to tell where the intersection points are in order to set up an integral. And then even then, we might want to decide to do this with horizontal rectangles or vertical rectangles. It's going to kind of depend on the situation. So we got to carefully do this. I do know that this first graph is just the standard graph of x squared, but moved 2 spaces to the left. So I'm going to start by sketching a graph of that. I'm going to give myself plenty of room for this too. 1, -2. And I'm just going to put a point here, a point at -3, 1, and -1, 1. And then points at 0, 4, and -4, 4. And I'm just going to kind of really carefully sketch that graph, because part of the challenge here will be to figure out where those intersection points are and how they play out with our graph. Y equals 0 is also one of our boundaries, which is the x-axis? No, the x-axis, where y equals 0, so that's a thing too. And then we've got the graph of 4 plus x, which is a pretty standard graph with a intercept of 4 and a slope of 1, so that's going to kind of come down here and intersect like this. 4 plus x. And that's kind of nice for us. I don't know why the y equals 0 is part of this problem, because we didn't need it. Yo.
I'm filling the water bottle.
Yeah. Mine's already full, otherwise I'd ask you to run for me too. Once you got this graph down, you can pretty carefully pick out, and you can test really quick in the math and make sure it works, what the intersection points are. I think this -3, -1, or -3, +1 works for both graphs. And if you spot check plugging in -3 there, I think you can confirm you get 1 out of both of those. And the other intersection point is 0, 4, like that. So this is a pretty straightforward problem once you get it all mapped out. Because all we're going to do here is I think we can do this with vertical rectangles, because the linear function is always on top of the quadratic function. So let's make this the integral from -3 to 0 of quantity 4 plus x minus the quantity x plus 2 squared dx. And since this is technically not calculator active, we're going to have to do a little bit of work here to get that to work. It's going to, in the end, be a quadratic expression with just something x squared plus something x plus something. But we're going to have to do a little bit of expansion and combining of like terms first before we do that. And I would not recommend taking the antiderivative right now, because we don't really have the tools for that yet. So let's start by doing a bunch of work expanding this thing out and bringing it together. Just the inside part. We've got 4 plus x hanging out there. If we expand x plus 2 squared, we're going to have, and it's all being subtracted, we would have x squared plus 4x plus 4. And then that's all being subtracted. So 4 minus 4 is going to cancel out. That's kind of nice. So it's actually going to be pretty simple. Let's see. 4 minus 4 will go away. We'll have negative x squared. X minus 4x is minus 3x. And that's all dx. And at this stage, we're going to do the standard antiderivative, plug in 0, plug in negative 3. We're just going to have to be really careful because there's subtraction involved here. So let's take our time and make sure we don't mess up along the way. The antiderivative would be negative x squared over 2, a really common antiderivative. Minus, let's see, we need x squared, and we need this to be 3 when you multiply it by 2. So 3 over 2 is a really good way to do that, like that. Oh, sorry, I misspoke, guys. This is x to the third over 3. And the idea is if you took the derivative and brought the 3 down and the 2 down, they would both cancel out and leave you with just negative x to the second minus 3x. That's kind of the plan. We don't need to put a plus c on this one because we're going to actually evaluate it from 0 to negative 3, which also in turn we have to remember that even though when we plug in 0, nothing happens, that unlike the previous problem, the order kind of comes in with us. So the first part of this is going to be 0. If you plug 0 into that expression, you'll get 0. So rather than writing it all out, I'm just going to put a 0 in there. We also have to do minus the same expression if we were to plug in negative 3. So let's be really careful about this. Negative 3 to the third over 3 minus 3 times negative third squared over 2. And be really careful. There's a lot of possible positive and negative things that can happen in here. So we're going to be really careful. 0 minus in parentheses. This first chunk, let's see, the 3's cancel out. The negatives cancel out too. Because it'll be negative 27 over 3, so it'll be positive 9. And then we got 9 times 3 is 27 over 2. Pretty sure that's right. 0 minus 18 over 2 minus 27 over 2 would negative 9 over 2. So it's going to be positive 9 over 2. I'm pretty confident about that. Yeah. If I zoom out so I can see the whole problem, you can see the whole process going from start to finish there. Now's a good time if you're watching this after the fact to pause this right on that screen. You can see everything happening, all the steps from start to finish on this. Start by graphing it, find the intersection points, set up your integral based on what's on top, what's on bottom, and then from there it's a lot of algebra steps happening from start to finish. Don't be intimidated. None of it's difficult. Just has to happen all at once. Let's go on to number 16 here, where it's going to get a little simpler for a second. 16 is probably the easiest question I've given you guys in a long time on anything. Find f prime if the original function is 2 square roots of pi. Well, the thing is that there's no x over here. This is a constant number. Since there's no x involved, f prime of x is just going to be 0, and that's all I have to say about this problem. The derivative of a constant number is 0. So there's no x there.
Oh, that's easy.
Ba-da-ba-ba. Easy peasy. 17 is also pretty simple, but you kind of have to realize what to do. And the thing about absolute value in calculus class is that there is no such thing as the derivative or antiderivative. Absolute value is often not differentiable because of its sharp, pointy corner. However, we can do this problem with some easy geometry, and that's exactly how we're going to solve it. We're just going to graph the absolute value of x minus 2, chop it into some triangles, and find the area of those triangles. So let's do that right over here in this space. We're talking about the... Is that the Twitter noise?
Yeah, I think. Or Samsung, I don't know.
Isn't it flipped? Because I thought the smaller number was on the bottom.
Oh, it is too. Yeah, I guess you're right. Good catch. I didn't even see that. I guess in the end of the day, we're going to find the integral from -2 to 4, and then find the opposite of it, whatever that is. Just one little extra trick.
I'm sorry, but I was...
No, I didn't even notice it. I didn't even see it. I think my brain auto-corrected it.
Well, because
When I teach English, I always tell kids to like read their paper upside down because your brain will skim over like little grammar mistakes and stuff you got, but if you read it upside down, it forces your brain to look at it differently, so you don't.
Wait, really?
Yeah.
Like upside down?
Yeah.
Or like upside down?
No, like upside down, like turning your paper upside down, because it's a proofreader's trick, because it helps you find like, if you're reading something really fast, your brain will just skim over and autocorrect mistakes, because that's what it does. It looks for patterns. So if you've got like, I don't know, the word weird with the wrong spelling or something in it, I don't know, it's really easy to skim over those mistakes when you're proofreading your work. Actually, just a little pro tip. Yeah. I should stop talking about English today because they're gonna make me teach English next year. And I got
a question, sir.
That's up.
Why are they making you do
They're not. I just don't want to.
Number 6.
They should never want me.
What is the fundamental theorem?
I'm actually in the middle of recording a video right now, Jeff, but we'll talk about that in just a moment.
Okay, no, I have a real question.
Okay.
So, when you're getting your antiderivatives, right,
Mm-hmm.
you have plus c at the end, right?
Correct. Well, it depends. Are you looking at a definite integral or an indefinite integral?
I think it's indefinite with no numbers on it.
Does it have numbers on it?
No.
Then it's an indefinite integral, and you must put plus c.
Sweet.
Is this the integral from -4 to 2? -2 to 4. Okay. Oh, that's silly. Oh, no. I graphed it wrong. I'm silly. Sorry, guys.
How is that?
It's positive.
It's been moved to the right 2 spaces. So here's my vertex. There's your graph. Puff, positive. Slope dude.
Can we watch the video?
I'm sorry, Abby. Slope dude didn't go to cool school to be called Slope man.
He should have been surfing if he sloped iron.
That's true. This is the integral from -2 to 4, right? I keep drawing this wrong. I'm all confuzzled over here.
I'm always
-2 to 4. There we go. That's what I want. Perfect. Should look something like that. We're doing the integral from -2 to 4 of the absolute value of x minus 2 dx. All right, so when we're looking at this from a triangle east perspective, we're going to have a 4 here and a 4 there. So the area of this triangle is 1/2 times 4 times 4, which is half of 16, which is 8. And this is a 2 and a 2, so that's going to be half of 2 times 2, which is half of 4, which is 2. And so this area under the curve ends up just being 10. The only little thing we need to remember is that the original problem asked us for the integral from 4 to -2, so the answer is -10. That's the only difference.
How does that work if you can't have
Because it's not actually the area. Area just helps to really model what's going on. It is adding up all of the possible values that are under this curve. So area is a helpful model for that, but it's not actually an area. So this ends up being -10. (18) and 19 are both pretty easy questions, especially because we don't have to evaluate anything, which is pretty typical of the AP test. They will give you a situation and ask you to just set up an integral. And that's reality too, because if you continue in your mathematics adventure and you go on into engineering or whatever, you'll often find that real physicists or whatever just let a computer do all the number crunching for them. You have to set everything up, but a computer can do most of this stuff for you. So in this case, we're going to have to split it up into 2 integrals, since g of x is on the top for the left chunk and on the bottom for the right chunk, and the reverse is true for the next part. F of x on the bottom, f of x on the top. So we'll do 2 separate integrals. The first one will run from 0 to 2. And in that little realm, from 0 to 2, it appears that g of x is on top, g of x minus f of x dx. And to that, we're going to set up a second integral from 2 to 4. And this one is going to be the opposite, f of x minus g of x dx. And that is the best way, I think, to answer question 18. If I was going to rewrite this question, I would say write an integral expression, because I don't like that it says write an integral, because it implies you can do it with one integral, and I don't think you can.
Is this test tomorrow?
Team test. Question 19 is going to be very similar. This is going to ask us to write an expression representing the shaded area shown from -3 to 4. And again, I believe those are the intersection points there and there. This one is also going to require 2 integrals because we have f of x on top for this first little chunk from -3 to 2. And then looks like h of x comes into the play and becomes the top function from 2 to 4. And g of x, the parabola, is always on the bottom no matter what. So setting this thing up, the first integral is going to run from -3 to 2. And it'll be f of x minus g of x. But then the next chunk of the problem is going to bring h of x into the picture. This is going to be from 2 to 4. And this is h of x minus g of x dx, like that. Pretty cool. And again, walk away, because you don't need to do anything else with this. And you know what's cool is we don't need to do number 20, because we are not talking about Newton's method in this course, because it's no longer part of the AP Calc AB curriculum, and we're not going to worry about it. So 20 we can forget about. What about number 10?
So
I'm going to stop this video so I can. I know, I saw that too. I did call about that on my. I think somebody had a stroke in the middle of this question, or maybe they started writing it and then halfway through they were like they forgot where they were. Maybe they went home. They went home and had a nap and had a dream about a barrel, and they came back and finished writing the problem. So yeah, I don't know what happened here. You substitute in your head the word shoe for the word barrel, or the word barrel for the word shoe. Whatever you want to do. Yeah, barrel falls off a rock climber. He's carrying a barrel on his back. Or maybe the rock climber is one of those like Bernese mountain dogs that has a little barrel on its neck.
Maybe a barrel is a kind of shoe.
Maybe a barrel is a kind of shoe that we don't know about.
Wait, maybe a shoe
Is a kind of barrel.
Wait, your foot goes in the shoe, therefore making it a barrel.
This is like, for example, a butt. A butt is a kind of barrel too. Hence the phrase Boston butt, which is actually a shoulder cut of meat, but they used to pack it into barrels. They would call it butt meat, but it's not actually butt meat. It was just packed into barrels called butts.
Is that just this? Is the video still going or no?
Oh, it is still going. I'm going to stop it.
Yeah.
There is a